Hey everyone, welcome to the Logarithms test review. I'll be going over each problem step by step to prep you for the test that you all are going to rock. Number 1 asks you to rewrite the following equations in logarithmic form. Draw a number line for each and estimate the value of x. So it asks 3 things of you on each of the parts. Let's look at part number A. 2 to the x power is equal to 34. A note I'm going to put up here about general exponential forms. Let's say b to the x is equal to c. To convert that into logarithmic form, we write log, and the base on the exponent is going to be your base in the log. The result you're trying to get to is going to be the bigger number of the log, and it's going to be equal to our exponent, which in this case is x. So when we look at part number A, to rewrite it, we have log. The base of 2 in our exponent is the base in our log of 34 is equal to x, our exponent. Okay, the next thing we want to do is to draw a number line. In this case, our number line is going to be multiplying by 2. So we start with 1. Awesome. Once we get to here, we need to estimate the value of x. So we realize that 34 is between 32 and 64. So in this case, it's between 4 and 5 swoopies. But it is closer to 4 because 34 is closer to 32. Okay, part B. 9 to the x power is equal to 14. So again, we rewrite that in logarithmic form. So we have our log base 9 of 14 is equal to x. Again, we do the same thing and we draw a number line. Our number line will be multiplying by 9. We always start with 1. Okay, because 14 is between 9 and 81, we know that the log is going to be between 1 and 2 swoopies. Eventually, it is going to be closer to 1 because 14 is closer to 9. Okay, part C. 5 to the x power is equal to 120. So again, we have to convert this into logarithmic form. Log base 5 of 120 is equal to x. When we draw our number line is going to be multiplying by 5. Okay, we know that 120 is between 25 and 125. So we know that the log is going to be between 2 and 3 swoopies. But it is closer to 3 swoopies because 120 is closer to 125. Next, part D, 10 to the x power is equal to 85. So we have log base 10, and because it's base 10, we don't have anything in our base area because that is implied. So log of 85 is equal to our exponent, which in this case is x. So then we're going to draw a number line that multiplies by 10. Start with 1. Okay, because 85 is closer to, because 85 is between 10 and 100, we know that the log will be between 1 and 2 swoopies. But it is going to be closer to 2 because 85 is closer to 100. So number 2 asks us to rewrite the following equations in exponential form. We need to draw a number line for each and then estimate the value of x. So we again have 3 things we need to do here in each part. Before that, I want to make another note. Now we're going to be converting the logarithmic form into its equivalent exponential form. So let's say we take a general logarithmic form. Log with the base of b, and the result is c, equals x. So when we drew our number line, we realized that the base of our log is the same thing as a base in our exponential. It's what we're multiplying the number line by. And we realized that since x is a number of swoopies, that's how many times we need to multiply by that base. That's our exponent, which is equal to c, which is the result we get to when we multiply b that number of times. So let's look at part A. Log base 8 of 66 is equal to x. So to convert it into exponential form, we realize that our base in our log is the same thing as our base in our exponential, 8. We need to figure out how many times it multiplies in order to get to 66. Okay, now we draw our number line. Our number line, again, like I said, needs to multiply by 8. We start with 1. Awesome. So since we know that 66 is between 64 and 512, we know that our x, or amount of swoopies, needs to be between 1, 2, and 3 swoopies. However, since 66 is closer to 64, we know that our x will be closer to 2. So part B tells us that log base 2 of 10 is equal to x. So to rewrite it, we realize that the base of the log 2 is our base in our exponent. We raise it to the x power, and that should give us 10. When we make our number line needs to multiply by 2. Since 10 is between 8 and 16, we realize that x needs to be between 3 and 4 swoopies. So part C says that log base 7 of 240 is equal to x. So to rewrite that in exponential form, we realize 7 to the x power has to be equal to 240. When we draw our number line, that multiplies by 7. We realize that because 240 is between 49 and 343, x has to be between 2 and 3 swoopies. Since 240 is closer to 343, x will be closer to 3. Okay, part D tells us that log base 3 of 78 is equal to x. So again, rewriting that, we have 3 to the x power is equal to 78. Then we make our number line that multiplies by 3. We have 1, 3. Since 78 is is between 27 and 81, we know that x must be between 3 and 4 again. However, since 78 is closer to 81, we know that x must be closer to 4. So 3 asks us to create a table of good values for the following log functions. In order for a table to have good values, we need to purposely pick our x values so that we get whole number y values. So just a general note, when we evaluate log functions, so let's take a general log function, log base b of x, we know that our x is the number we get to on the number line. Our b is the number that we're multiplying by on the line. But more importantly, that c is the number of soupies it took to get to x. It's equal to 2 times log base 6 of x plus 8. So let's pick some x values that we can plug in to get some y values. So when we look at inside the parentheses, that is going to be equal to the number on the number line. In this case, it's x. So when we draw a number line that multiplies by 6, we realize that any number on the number line is going to work for our x. In this case, I'm going to pick 1/6, 1, and 6. But any value that's on the number line that's multiplying by 6 will work for x. Then we need to figure out what our y value is going to be. In this case, that's going to be what we get out when we substitute x. Let's look at x equals 1 over 6. From 1, we realize that it takes 1 swoopie to the left, so we know that our number of swoopies is -1. But we're not done yet. We have to take the -1 and multiply it by 2 to get -2. We add 8 to give us 6 as our y. Let's do the same thing to x equals 1. It takes us 0 swoopies to get to 1. From there, we have to multiply by 2 to give us 0. Plus 8 gives us 8. Now, with x equals 6, it takes us 1 swoopie to get to 6. Multiply by 2 to give us 2. Plus 8 gives us 10. Now we're good to go for f of x. We've got our x and our y values. For g of x, we do the same thing, but now it's equal to -4 times log base 3 of x plus 2. Again, we look at what is inside our parentheses. That is going to give us the number on the number line, which in this case, it's x again. So when we draw our number line that multiplies by 3, we realize our x can be any number on the number line. In this case, I'm going to pick 1/3, 1, and 3. But as long as you got a number that's on the number line, you are good to go. Then we want to get our y values when we plug in x. I'm going to draw a box around the log because that will tell me the number of swoopies. But there's stuff outside this box, which means there's stuff we need to do to our number of swoopies. So we're going to be multiplying by -4 this time, and then adding 2. So let's find our number of swoopies when x equals 1/3. Takes 1 swoopie to the left, so we know that our number of swoopies is -1. From there, we have to multiply by -4 to give us 4. When we add 2, that gives us 6 as our y. Next, let's move on to x equals 1. It takes 0 soupies for us to get to 1. When we multiply by -4, we get 0. Adding 2 gives us 2. We've realized that the y values are decreasing because of this negative right here. This is going to tell us that our graph is going to be decreasing. Okay, now let's look at x equals 3. It takes us 1 soupy to get to 3. When we multiply by -4, we get -4. Adding 2 gives us -2 as our y value. Okay, now let's look at h of x. That is equal to log base 5 of x minus 3. Now, wow, let's look at what's inside of parentheses. It's not just x anymore. It's x minus 3. So we know that the parentheses will give us the number on the number line, or what's in the parentheses, excuse me. So let's draw our number line first. Numbers on the number line include 1/5, 1, 5, 25. So if I pick some of the values on the number line, let's say I picked, picked 1, 5, and 25, we need to realize that that is not our x. Our x needs to be what, when it's subtracted 3, gives us 1, 5, and 25. So let's take our value on the number line of 1. We know that x needs to be 4 in order to get 1. So our y, let's look at the function. Our y values are actually just given by our log. Our y values do not change from the number of soupies. So when x equals 4, the number on the number line is then 1. So to get to 1, it takes 0 soupies. Okay, so when we want the number on the number line to be 5, we know that x needs to be 8, because 8 minus 3 is 5. And if we look at our number line, it takes 1 soupy to get to 5. Our x then, in order to get 25, is 28. And the number of soupies it takes to get to 25 is 1 and 2. Let's take a look at number 4. Number 4 asks us to describe the properties of the logarithmic function graph below. So let's take a look at the domain. That tells us our x values. In order to look at our x values, I will look at the graph from the leftmost point all the way up to a rightmost point. In this case, our x gets really, really close to 0, but doesn't touch it and goes all the way up to infinity. So to show that it doesn't include 0, we use the soft bracket. We go all the way up to infinity. The range tells us our y values. So our y values are given by looking at the bottommost point of the graph and then going all the way up to the top. So with logarithmic functions, we know that we can go as negative as we want. So we know that the graph goes from negative infinity and it keeps increasing. It goes all the way to infinity. The asymptote, again, tells us the x value that the graph does not touch but gets really, really close to, and that would be x equals 0. Okay, so now we identify if the graph is increasing or it's decreasing. If we were tracing the graph from left to right, we realize that the graph is increasing throughout its domain. So it's increasing from 0 all the way up to infinity. Because it's increasing all throughout its domain, we know that there is no decreasing interval. So now let's take a look at number 5. It asks us to describe the properties of the logarithmic function graph below. So again, we're going to be identifying the domain, which is our x values. If we go from our leftmost value and go all the way right, we realize that our x values start from 2, but not including 2, and goes all the way to infinity. Our range, which is our y values, we look from our bottom to our top. Because it's logarithmic, we know that our y values will be covered from negative infinity to infinity. There is no restriction. Again, our asymptote tells us the x value that the graph gets really, really close to but doesn't touch. In this case, the x value is 2. When we trace the graph, we realize that the graph is increasing all throughout its domain. So now the graph is increasing from 2 to infinity. Keep in note that when we're writing the increasing or decreasing interval, we always have to use our x values. Because the graph is increasing all throughout its domain, there is no decreasing interval. Now let's take a look at number 6. Number 6 asks us to solve the following exponential equations for x. We need to round our answers to 3 decimal places. So whenever we want to solve for x, the first thing we want to do is isolate the exponential part of the equation. So in part A, the exponential part is 4 to the power of 2 times x. We want to isolate just that. So in order to do that, we want to subtract 5 from both sides. When we subtract 5 from both sides, we end up getting 2 to the power of 4 to the 2x is equal to 20. Now again, we want to isolate the exponential part of the equation. So in order to do that, we have to divide 2 from both sides. And that gives us 4 to the 2 times x alone on the left-hand side. And that has to equal to 10. From here, we will need to rewrite this equation in logarithmic form. So just like we did in number 1, we realize that the base in our exponent, which in this case is 4, is also the base in our log. The result then is 10, and we set that equal to our exponent, which in this case is 2x. So our natural thing to do is try to plug in the calculator to evaluate log base 4 of 10. When we try to plug it into our calculator, however, we realize that we cannot because our calculator only evaluates logs with a base of 10. So we do this procedure called change of base. So the change of base tells us we can take the log of our bigger number of 10 and divide that by log of our base 4. Again, we set that to 2x. Okay, so now let's take a minute to plug that into our calculators. We end up getting that 1.6609 is equal to 2x. From there, we are not done because we have not solved for x. To get x alone, let's divide 2 from both sides, and that'll end up giving us x is equal to 0.830. Yay! Awesome. Now let's move on to B. B gives us the equation of 7 to the power of x plus 1 minus 8 will give us 73. So again, we want to isolate the exponential part of the equation. To isolate that, we have to add 7 to both sides. Oh, sorry, not add 7, add 8. Then we have that 7 to the power of x plus 1 has to be equal to 80. Now we have isolated the exponential part of the equation. From there, we can rewrite it into logarithmic form. So again, we have that the log of our base of 7 we're trying to get to 80 will give us our exponent, which is x plus 1. So let's take a minute to solve for log base 7 of 80. We cannot plug that into our calculators. Again, it needs to evaluate in a base of 10 scale, so we have to change the base. We do this by taking the log of 80, our result, and we divide that by our log of the base. We set that equal to x plus 1. We should end up getting that 2.2519 is equal to x plus 1. Now we are not done solving for x. We need to get x alone. To do that, let's subtract 1 from both sides. We end up getting that x is equal to 1.252. Okay, now let's look at part C. 2 times 5 to the power of x plus 8 will give us 120. So again, we want to isolate the exponential part of the equation, which in this case is just 5 to the x power. To do that, we will need to subtract 8 from both sides first. We get that 2 times 5 to the power of x is equal to 112. From there, we still have not isolated the exponential part. So in order to do that, let's divide by 2 from both sides to give us 5 to the power of x is equal to 56. Okay, so now we realize that by converting it, we have that log base 5 of 56 is going to give us our exponent of x. So again, we cannot plug this into our calculators. So what we have to do is to change the base. We have log of our result, which is 56. And we divide that by log of our base of 5. We set that equal to our x. We get that x then is equal to 2.507. 7 asks us to solve each equation for x. So let's take a look at part A. Immediately, we notice something special about part A. We notice that there is an exponent on both sides. When we notice this, we need to make sure that our bases are the same in order for us to start solving. So let's take a look at the bases now. We have 9 left-hand side and 27 on the right-hand side. We notice that they share a common factor of 3. So let's rewrite 9 using our common factor of 3. So we know that 9 is also equal to 3 to the second power. And from there, we have to raise it to our exponent, 4x plus 1. Now let's look at 27. When we look at 27, we can rewrite it as 3 to the third power. And again, we have to raise that to the power of 3x minus 2. When we raise a power to a power, what do we have to do with our exponents? We end up that we have to multiply our powers together. When we multiply these exponents together, we need to make sure that every component receives love from the 2 and the 3. So in this case, 4x needs to receive love from 2, and 1 needs to receive love from 2. So we keep the base the same. We have 3. And when 4x receives love from 2, we multiply those together to get 8x. And then 1 receives love from 2, so we get plus 2. Here, we have our base as 3, and 3 times 3x is 9x, minus 2 times 3, which is 6. Now that our bases are the same, we don't have to worry about them anymore, and we can just set the exponents equal to each other. So we have that 8x plus 2 is equal to 9x minus 6. So now we have to set like terms. We have to move like terms to one side. So in order to get 8x and 9x together, I subtract 9x from both sides. I end up getting 8x minus 9x, which is negative x, plus 2 is equal to negative 6. Then I'm going to get rid of the 2 on the left-hand side by subtracting both sides by 2. Then we end up getting negative x is equal to negative 8. Dividing both sides by negative 1, we get x equals 8. We could verify that x equals 8 by plugging in 8 for x and seeing if both sides equal to each other. Next, let's look at part B. So part B shares this unique characteristic where both sides have an exponent. So again, we have to make sure that both sides share the same base. So let's look at our base 8 and 1 over 64. So we realize that we can rewrite these using the base of 8. That means we don't have to rewrite the left-hand side at all. We get 8 to the power of x plus 2. We also know that 1 over 64 is equal to 8 to the negative second power. So we have that 8 to the negative second power is raised to the fifth power. So now we can get rid of our exponent. Now we can get rid of our base and just focus on the exponent. That x plus 2 is equal to negative 2 times 5. We have x plus 2 on the left-hand side is equal to negative 10 on the right-hand side. To get x alone, we subtract 2 from both sides, leaving us with x is equal to negative 12. Again, in order to verify that our answer is true, we can substitute negative 12 for x and ensure that both sides are equal to each other. So when we look at part C, again, it shares the same characteristic as A and B. that both sides have an exponent. So when both sides have an exponent, we have to make sure that both sides share the same base. In this case, we can see that both can share the same base of 2. That means on the left-hand side, we do not need to rewrite it. It already has that base of 2. But we know that 4, we can rewrite as 2 to the second power. And we raise that to the power of x plus 4. Then, because our bases are the same, we can ignore our bases and just focus on our exponent and set those exponents equal to each other. So we have x plus 2 on the left-hand side is equal to 2 times x plus 4. Then we distribute that 2 on the right-hand side, and we get that x plus 2 is equal to 2x, because 2 times x is 2x, plus 2 times 4, which is 8. Then we move all the x's to one side and all the constants to the other side. To do so, I'm going to subtract 2x from both sides. X minus 2x is equal to negative x, plus 2 is equal to 8. Now we can subtract 2 from both sides to leave us with negative x being equal to 6. To get to x alone, we need to divide by the negative 1, and we get that x is equal to negative 6. In order to make sure that x is equal to negative 6, we could plug in negative 6 for x and make sure that both sides are equal to each other. Okay, part D is a little bit different from part A, B, and C. We realize that the equation is written in logarithmic form. So, whenever it's in logarithmic form, we can use a number line to help us find our x. So let's recap. We know that 5 is a number that we're multiplying by on the number line. We know that x has to be the number that we're getting to after 2 amount of swoopies. So when we draw our number line that multiplies by 5, we know that the number we have to get to is done after we get 2 swoopies. So we have that x is equal to 25. We could have also figured this out by using without using the number line, by rewriting this equation into a exponential form. Again, the base on our log becomes the base on our exponent. We have that 5, and the swoopies end up being our exponent. We set that equal to the result. So, again, x equals 25. So part E and F are very similar to D in that they are all written in logarithmic form. So in order to solve equations that are in logarithmic form, first we want to isolate the log. Just like we realized in D, it was really easy for us to find x once we got log alone. So in order to get this log base 4 of x plus 2 alone, we need to subtract 10 from both sides. When we subtract 10 from both sides, we get log base 4 of x plus 2 on the left-hand side and 2 on the right-hand side. Now, it becomes really easy for us to find x. Let's highlight some features of this logarithmic equation. When we draw the number line, we realize that 4 is the number we're multiplying by. What's inside the parentheses is the number on the number line. And then 2 is our number of swoopies. So from here, let's draw a number line that multiplies by 4. The number on the number line we get to in 2 swoopies. So we realize the number on the number line needs to be 16. Since x plus 2 tells us our number on the number line, we realize that x plus 2 must be equal to 16. So we're not done yet. We still need to solve for x. So in order to solve for x, we subtract 2 from both sides, leaving us with x equals 14. In order to verify that that's true, if we plugged in 14 for x, we notice that both sides are equal to each other. Now let's look at f. Looking at f again, let's isolate what's inside our log. We have log base 5 of 2x minus 3. Our job is to get that alone. In order to get that alone, since there's that 3 that's multiplying the log, we need to divide by 3 on both sides. This will undo the multiplication, leaving us with log base 5 of 2x minus 3 on the left-hand side is equal to 3 on the right-hand side. From there, let's identify the same features. We know that 5 is a number that we're multiplying by. We know that 2x minus 3 is the number on the number line. And we know that 3 is the number of swoopies it took to get there. Okay. So now let's draw the number line that multiplies by 5. In 3 swoopies, we know that the number on the number line has to equal to 125. So we have that 2x minus 3 is equal to 125. We could have also figured out that 2x minus 3 is equal to 125 by realizing that 5 to the third power is equal to 125. And that needs to be equal to what is inside our parentheses. Okay? So now we solve for x. In order to get x alone, first, we have to add 3 to both sides. We end up getting 2x on the left-hand side and 128 on the right-hand side. Our final step in getting x alone is dividing by 2 on both sides. So we end up getting that x is equal to 64. Yay! So in order to verify that this is true, all we would have to do is plug in 64 for x and know that both sides will equal to each other. Thanks for watching.